Good evening all. Welcome to the Quantitative Session 4. So presentation includes 10 minutes presentation and 5 minutes question answer session. Total 15 minutes. Please keep the time. First participant CP18 Ashaji Pillai. Ma'am, share your slides.
Yes. Shall I start?
Yes.
Okay.
So we can start for 10 minutes, right? 2 minutes. 2 minutes more.
Okay, sir. Okay, sir.
Okay. Start.
Okay.
Start now, please start.
Good afternoon. The title of the presentation is On the Bitopological Space Associated with a Three-Uniform Semigraph. We shall start with some basic definitions. Semigraph. A semigraph G is a pair Vx, where V is a non-empty set whose elements are called vertices of G, and X is a set of n-tuples called the edges of G of distinct vertices for n greater than or equal to 2, satisfying the following conditions. Any two edges have at most one vertex in common. Two edges U1, U2, etc. Un and V1, V2, etc. Vm are equal only if n equals m and either ui equal to vi or ui equals vn minus I plus 1. If E equals U1, U2, etc. Un is an edge of the semigraph G, then U1 and Un are called the n vertices of E and the other vertices are called the middle vertices. The number of vertices on an edge is called the cardinality of that edge. For example, consider this semigraph. The edges are U1, U2, U3, U3, U4, U4, U5, U5, U6, U3, U6, U1, U6, U4, U4. For the edge U1, U2, U3, U1 and U3 are the n vertices and U2 is the middle vertex. The vertices U1, U2, U3 are adjacent, of which U1 and U2 are consecutively adjacent. Similarly, U2 and U3 are also consecutively adjacent. A semigraph in which the cardinality of each edge is the same is called a uniform semigraph. If that cardinality is K, we call that graph a K-uniform semigraph. The next definition we need is a bitopological space. A non-empty set X with two distinct topologies τ1 and τ2 defined on X is called a bitopological space denoted by X, τ1, τ2. Now, we have to define a bitopological space on a 3 uniform semigraph. For that, we call the vertex set of the 3 uniform semigraph as B. Let it be 1, 2, 3, 4, etc., of which 1, 3, 5, etc. are the end vertices, and 2, 4, 6, etc. are the middle vertices. The collection of all end vertices is denoted by E, and the collection of all middle vertices is denoted by M. Next, define an outlying neighborhood of each vertex as follows. For each vertex I, the outlying neighborhood NIO is defined as NIO equals V minus CI, where V is the vertex set and CI is the set of vertices which are consecutively adjacent to E. Now consider the collection tau E equals intersection I belongs to E, power set of NIO, and tau M equals intersection I belongs to M, power set of NIO, where P of NIO denote the power set of NIO. These tau E and tau M are discrete topologies on E and M respectively. E is the collection of all end vertices and M is the collection of all middle vertices. Now take the union of these sets, tau E and tau M, with the vertex set. We get other two sets too, tau E dash and tau M dash. Tau E dash equals V union tau E and tau M dash equals V union tau M. Tau E dash and tau M dash are topologies on the vertex set V, and these topologies are defined on the same vertex set V. So V together with these two topologies form a bitopological space. This is an example. This is a semigraph, the uniform semigraph. The cardinality of each edge is 3. For the first vertex I, we define the outlying neighborhood as, first we have to find out the consecutively adjacent vertices, which are 2 and 6 here, and then remove those consecutively adjacent vertices from the vertex set. So we get 1, 3, 4, 5. Similarly, we can define the outlying neighborhoods of all other vertices. Now we get tau E is as the discrete topology on the end vertices and tau M as the discrete topology on the middle vertices, collection of all middle vertices. Take the union with the vertex set, tau E dash equals tau E union V, the whole vertex set, and tau M dash equals tau M union V. These two are the topologies, two different topologies defined on the same vertex set V. So V tau E dash, tau M dash is a bitopological space. Now results. All the definitions used in these are taken from the paper Bitopological Space written by J.C. Kelly. First definition, any subset A of a bitopological space X, tau I, tau J, I, J equals 1, 2, I not equal to J is said to be IJ semi-open if A is a subset of closure with respect to tau J of interior with respect to tau I of A. We can prove that a subset A of the bitopological space that we have defined on V, that is V tau E dash tau M dash, is 1, 2 semi-open if and only if A is a subset of the end vertices, the collection of all end vertices, that is E, where tau E dash is taken as tau 1 first topology and tau M dash is taken as the second topology. Similarly, a subset of the bitopological space V tau E dash tau M dash is 2, 1 semi-open if and only if A is a subset of EM, that is collection of all middle vertices. Second definition, any subset A of a bitopological space X tau I tau J is IJ pre-open if A subset of interior with respect to tau I of closure with respect to tau J of A. A subset, next theorem, a subset A of the bitopological space V tau E dash tau M dash is 1, 2 pre-open if and only if A is a subset of E, and 2, 1 pre-open if and only if A is a subset of M. Third one, any subset A of the bitopological space X tau I tau J is said to be IJ alpha open if A is a subset of interior with respect to tau I, closure with respect to tau J of interior with respect to tau I of A. Here also we can prove that a subset A of the bitopological space V tau E dash tau M dash is 1, 2 alpha open if and only if A is a subset of E, and 2, 1 alpha open if and only if A is a subset of M. A bitopological space X tau I tau J is said to be pairwise extremely disconnected if closure with respect to tau j of A is tau I open for each tau I open set in X. Theorem, the bitopological space that we have defined here, that is V tau E dash tau M dash, is pairwise extremely disconnected. Next result. Definition, any subset A of a bitopological space X tau I tau j is said to be Ij dense in X if closure with respect to tau I of closure with respect to tau j of A equals the whole vertex set. Every non-empty proper subset of the bitopological space V tau E dash tau M dash is 1,2 dense and 2,1 dense, where tau E dash is taken as the first topology and tau M dash is taken as the second topology. Next definition is any subset A of a bitopological space X tau I tau j is said to be Ij nowhere dense in X if interior with respect to tau I of closure with respect to tau j of A equals 5. Otherwise, A is said to be somewhere dense. Only the null set will be nowhere dense. The theorem is a subset A of the bitopological space V tau E dash tau M dash is 1,2 nowhere dense if and only if A equal to 5. And 2,1 nowhere dense if and only if A equal to 5. These are the references. Thank you.
Thank you, ma'am.
Thank you, sir.
Any queries? No queries? Okay, thank you, ma'am.
Thank you, sir.
Next participant, CP19, Sanuj B. Sanuj sir. Next participant, C19, Sanuj B. Sir, can you hear me? Hello, Sanuj sir. Please unmute. Sir, can you hear me? Hello. Okay, next participant, Jagashnavi, CP20. Sir, are you ready?
Yes, sir.
Okay, okay.
Hope I'm audible.
Yes, yes, sir.
So I cannot share my screen because it is already shared
Okay, okay.
by Sanu sir.
Sanu sir, please stop the share.
Okay, thank you.
Okay, sir.
Let me try to share my screen.
Okay, okay, okay.
Hope it is visible.
Yes, yes, visible.
Okay. So good evening, everyone over there.
Just a minute,
Online.
sir. Just a minute. We can start at this 4:25, right? 2 minutes more, right?
Okay.
Okay, sir. If you are ready, you can start, sir.
Okay, sir.
Okay, okay.
Okay. Good evening, everyone over there. So the title of the presentation I'm going to make is on a paper named on jumping graph grammars. It is co-authored by Dr. Lisa Matthew and Dr. Juby Matthew. Myself is Jaya Krishna. We all are from Amaljodi College of Engineering, Kandapalli. So this is the overview of the presentation. We'll be having an introduction to graphs, graph grammars and all. Then we'll be moving on to what actually is jumping grammars. Then we show what actually is an NCENC graph grammar. Then the jumping version of that thing and some variants of NCENC jumping graph grammars. So we'll wind up with some research interests and applications of whatever we have going to discuss right now. So as an introduction, graphs, as you all know, is a meaningful and mathematically intuitive way to represent a set of objects as nodes and their relationships as edges. Graph rewriting systems actually dynamically model the evolution of the graphs. Graph grammars obviously is capable of modeling the generation of various families of graphs. These are some areas wherein which graph grammars are totally relevant to. One is computer science, wherein which we have n number of applications of pattern recognition, starting right away from pattern recognition till designing known sequential kind of systems. When it comes to pure graph theory, we have grammatical manipulation of graphs, then convenient processing of multidimensional pattern classes and all. When it comes to biology, we can do several operations based on graph grammars. One is developmental description of an organism, simply simulating how an organism has been born till death, and how you can serve as it can also serve as a precise description of development stages of an organism. Then it can mimic some processes like cell division, genetic regulations, and all. It can even have some hierarchical lookup of a class of animals or class of organisms. So graph grammar, the base definition is it is a typical graph grammar consists of a main graph called the host graph and a set of transformation rules of the form P of MDE, where M is a mother graph to be replaced, which is present in the host graph H, and D is the daughter graph, which gets embedded after replacing your mother graph. You have E, which is the embedding mechanism that we use. Depending upon the embedding mechanism that we have several kind of graph grammars. So one such example is given over here. I have a graph grammar of the form sigma equal to GG equal to sigma delta gamma P and S, where sigma is the node labels, delta is the terminal node label, and gamma are the edge labels, and P1 and P2 are the rules used for building up this graphs in the graph grammar. You can see C1 and C2, these are the two connection instructions that we use for doing this embedding process. So this this grammar is capable of generating any kind of complete graphs Right now, I'll show how to generate a K4 graph. So these are the first two rules. It starts from a single node, that is S, that is the starting node. Then you use production rule number 1 to convert or replace the node S with a graph, that is AS. A to S is connected with an alpha edge. Then again, I repeatedly use this rule so that the capital S labeled node gets removed and replaced with a graph called AS. So you can see the one which is in red are the connections established based on the connection instructions that has been shown on these production rules, which is far right of each production. Similarly, this process goes on and ends up in a complete graph of size 4. So a glimpse on what actually is jumping grammars. Jumping grammars are introduced as part of linguistic kind of analysis done on or grammars or English grammars that we have. So it is of the form NTPS. N is a finite set of non-terminals, T is a finite set of terminals, P set of production rules, similar to that of what we had in our automata kind of stuff. And S is the start symbol, and T is the set of terminal symbols. So the derivations of strings can take place in these three fashions. One is a normal conversion, where in which you will convert a U to a V using some rule P. Or you convert from X to Y using you convert using X goes to Y, that is a production rule that we have. So if you have a string U of the form W X Z, then after applying P, it will get converted to V of the form W Y Z, X getting converted to Y. When it comes to jumping grammars, you can have two kinds of jumping, left jumping and right jumping. If your jumping is of the form U to V using left jumping, then if the string was of the form WTXZ, after applying X goes to Y with left jumping, you will replace X with Y and move towards left, that is the left of T. This is what happens. Right jumping is similar to jumping towards right. So this is a base information of how jumping grammars works. And recently we have introduced a new class of graph grammars, a new category of graph grammars called non-confluent edge and node controlled embedding graph grammars. So where in which previously you have seen some graph production rules generating a graph, K4 graph. What here we do is we apply a restriction on how to use the production rules of that particular graph grammar. So if you apply a restriction in the form of a regular expression, this production rules can be effectively utilized to generate the desired graphs that we have. So here it is a 7-tuple information, set of node labels, set of terminal node labels, gamma is a set of edge labels, then omega is a set of terminal edge labels, P is the graph production rules, S is the start node or initial graph, and R of P, as we know, is the regular expression used to control these production rules. So this is how a production rule look like. P is of the form A can be rewritten as D, C. D is a daughter graph, and C is the connection instruction for the production. So it is of the form, C is of the form A, P bar, Q alpha, where P and Q are edge labels. A is the node label of one of the neighbors of the mother node, and alpha is a node in the daughter graph P. So we have an interpretation for this thing. We find an edge labeled P in the host graph, which has actually connected to the mother graph, which got removed. And this P will get connected to Q, or this P has a connection to Q with label alpha once you embedded the daughter graph D using the connection instruction C. So the same K4 graph can be designed using this grammar. You can see R of P, that is the regular expression given. The regular expression is of the form P1 star P2, that is 0 or more times the first production rule. Along with that, you have to apply the second production rule. So this is an NC graph grammar generating K4 graphs. You can generate any complete graph using this particular graph grammar. Depending upon the number of times you use the production rule P1, you get enough amount of complete graphs. So all the things which are in red is the ones which got embedded, the new connections established once we apply each production rule. So here it is of the form to get K4, you apply P1 3 times, that is P1 raised to 3 followed by P2. That is a regular expression. So that is a controlled graph generation. Then coming on to our new graph grammar, that is jumping graph grammars. So jumping graph grammars actually is of the form sigma, P, C, and S, where sigma is the finite set of node labels, P is the finite set of production rules, P is of the form M goes to B, where M is a mother graph to be replaced by a daughter graph. C, you obviously you have a connection instruction to connect your daughter graph to the rest of the host graph. Then the connection instruction has an extended capability over here. Previously, the connection was done by having those nodes which were actually connected to the mother graph, which got replaced with that of the daughter graph. Here you can connect to any other nodes which are present in the remaining of the host graph with that of the daughter graph. So that is why you have GS minus N. That is the remaining of the host graph. So for demonstrating jumping graph grammars, we have defined a graph called B graph. B graph is of the form BK, K greater than or equal to T. You have 2K vertices and the edges are of these forms. You will be having edges of the form V2I minus 1, comma V2I, V2I minus 1 to V2K minus 1, V2I to V2K, where 2 less than or equal to or I varies from 2 to K minus 1. Another set of edges of the form V2I minus 1. Hello?
Time over. Please conclude.
Okay. I was just supposed to take 10 minutes, right?
So it is 10, it is 10 minutes. It is 10 minutes.
Okay.
Okay.
Can I take a couple of minutes?
Okay. You try to complete as early as possible.
Okay. So this is a B graph which is generated using the graph grammar, jumping graph grammar. So the connection instructions are over here of the form AA, BB, XA, and YB. AA and BB are the normal connection instructions, and XA and YB are the jumping instructions. I'll just show how it is being created. This is the start graph. These are the production rules, and this is how it gets generated. You add one XY node, and you jump from X to all the A's and Y's to all the B's. So this is how it gets generated. We have another version of jumping graph grammars of the form NC jumping graph grammars, wherein which you apply restriction on how to apply the production rules. So this is another graph, wheel graph, which is generated using our extended version, that is NC jumping graph grammars. So you can see that finally from the node labeled capital S, we have a connection, a production rule of the form AC. And from C, you suddenly have a connection going to all other A's, jumping to different A's. Similarly, you have some star graphs which are getting generated using distance-based jumping, where in which you have a connection instruction with the node labels, the edge label, and a distance. That is, yeah, that's it. Yeah, I'm going to conclude. These are the further research areas wherein which you can have modeling of biochemical structures, lock and key based game structures, and all. These are the references that we have used. And thank you. And sorry for taking 2 more minutes.
Okay, no problem, sir.
Thank you, sir.
Any queries? Okay. No queries? Okay, thank you. Thank you, sir.
Thank you.
Okay.
I'll stop the sharing.
Okay. Please rejoin. All the participants should rejoin the Zoom link once again.